So let's take a look at the location where we stopped our class last week. Right? This is what we have last week. Okay, so basically, depending upon the condition of the flow, you can simplify the Navier Stokes. Rather than Navier Stokes, it is a fully conservation of mass and momentum. Okay, so it's a full conservation of mass and momentum. And for some specific cases, you can simplify it. In this case, you know that the flow is only one direction, so phi and W is 0. It is steady, so everything with regards to time becomes 0. And then it is incompressible, which means rho is constant, so you can take it out, right? Since du dx plus bv dy plus dw dz is equal to 0, and phi and w is 0, you have du dx is equal to 0. Okay, so basically, you know that for every flow, u is a function in x, y, and z. Phi is a function of x, y, and z, and w is function of x, y, and z. Remember this. So even though you have only u, not necessarily that it is a function of x only. No. It can be a function of y and z. In this case, your phi is 0, so everything is 0. W is 0, so it's 0. Because there is no flow to the top, no flow to the side. Only flow to the front, right? But even the flow to the front, the flow in this location, I mean my flow in this location can be different with the flow in this location, can be different with the flow on that location. My flow here can be 3 meters per second, over here can be 4 meters per second, because it can be a function of x. Okay? But since you have z is infinite, you know that it is not a function of z. Because the side wall is not there, so the flow will move along the z at the same speed. That's why it is not a function of z. So it is a function of x and y. But from your conservation of mass, you know it is not a function of x. So it ends up u is only a function of y. Okay? Having said so, you know that if du dx is 0, so d squared dx squared, which is basically d dx of du dx, which means the derivative of u, right? The derivative of u is 0, so the derivative of those things is of course 0, right? So accordingly, you can cancel out according to that, and you will end up having those things. 1, 2, 3, a very simple one. This equation giving you the information that the pressure in the z direction is constant, not 0. It is constant, which means the pressure over here and the pressure over there and the pressure over there is constant. Right? These tell you, if you integrate it, that the pressure in the y direction is a function of depth, which is basically your hydrostatic pressure. This F1x is nothing but your pressure at the top level. Okay? So for a non-moving flow, let's say for a non-moving flow, this u is 0, right? So your flow will just govern by this thing. Right? Which means Navier Stokes can also be implemented for a static fluid. It can. Which gives you the hydrostatic pressure equation. That's all. Right? Whereas this one is when you have the flow. Okay? Most of the time you don't care about this, you want to know about that. Now we have stopped in this equation last week. Now, if you look at this one, why I changed from those, what you call it? partial derivation into the ordinary derivation is because u now is only a function of y. So you don't have to use partial derivation. Since you are having this, you can easily double integrate it to get the value of u. Okay? So now what I'm doing here is I move this to there, or yeah, you can move this to there. So you get mu d square u dy square. The mu is actually over there. So I move that mu to the bottom side. So you got d square u dy square is equal to 1 over mu dp dx. Why this d is still there? Because pressure is also function of y. You cannot change that into dp dx, normal, ordinary. Okay? So you are UTP student, straight A student, so you should be able to double integrate it easily, right? Just integrate once, you get du dy. Why there is C1 here? Because this thing will be vanished when you take a derivative, right? So when you do integration, you have to reinstate it. So C1 has to be there, right? Not finished, you double integrate it, you find this one. So this one, usually if you learn calculus or ODE, this one is the so-called a general solution. This one is quite common. This one usually has a family of solution, right? Depending upon your C1 and C2. If you remember that. If you don't remember, no worry, no problem. Okay, just look at it. This is how it looks like. Now, this one is not finished yet. You still have C1 and C2 which is unknown. So how do you get those C1 and C2? The boundary condition. In this case, do you remember your boundary condition is? Because it is a function of y, right? Which means your boundary condition has to be in the y direction. You are not talking about inlet or outlet, but you are talking about the bottom wall and top wall. You know why? Because it is function of y. That's why you choose y. Okay? So, applying the boundary condition, due to the no slip condition, because both of the wall is at a stationary condition, which means it is not moving, u is equal to 0 at the bottom wall surface, and u is equal to 0 at the top wall surface. Okay? Depending upon the location, this y can be 0, it can be minus h. This one also, it can be h or it can be 2h, depending on how you define your drawing. That's why in the SOP, you see that? You need to follow whatever diagram that you have decided. If you decide the head is 2A, 2H, you need to follow 2H. If it is S, you need to follow S, right? Up to you. Any question till this point?